The AP Physics 1 equation sheet looks like a foreign language, but you don't have to memorize every variable to succeed. To cut through the noise, you need a diagnostic heuristic. Nearly every problem on this exam falls into one of three distinct buckets. Bucket 1 is forces, analyzing motion at a specific moment. Bucket 2 is energy, tracking state changes from start to finish. Bucket 3 is momentum. During collisions, forces are messy, but momentum tracks the system cleanly before and after the interaction. Identifying which of these three buckets a problem belongs in reveals the specific mathematical path to the solution. Kinematics is the baseline vocabulary we use to describe this motion. One rule answers a massive slice of the multiple choice section. When an object's velocity and acceleration point in the same direction, it speeds up. When they point in opposite directions, it slows down. Projectile motion consists of two independent linear motions happening at exactly the same time. The horizontal speed stays constant, while the vertical speed is governed entirely by gravity. These two components share only one variable, time. Forces are the causes of motion. To map them, you must start every problem by drawing a free body diagram. Gravity points straight down, the normal force points perpendicular to the ramp, and friction points up the incline. The rubric is strict. You will lose points if you draw force components directly on the central object. Keep components on a separate sketch. The same logic applies to circular motion. Centripetal force is not an independent entity you add to a diagram. It is a label for whatever physical force happens to be pulling the object inward, whether that's tension, friction, or gravity. Master the rules for a simple, single dot first. This foundation allows you to solve the complex, moving systems that make up the course. Energy conservation acts as a ledger. As the sphere drops, potential energy trades places with kinetic energy. The total never changes. Friction acts as a leak. Sliding across a rough patch converts mechanical energy into heat. The total drops permanently. For systems involving sudden impacts, energy calculations often become difficult to track. In these cases, switch to momentum to see how two bodies exchange motion. Look at this comparison. On the left, we have an elastic collision. The objects bounce, and the kinetic energy bars stay level. On the right is an inelastic collision. The objects stick together, and the kinetic energy drops. In both cases, momentum is conserved, but energy is only preserved in the elastic bounce. To change an object's momentum, you apply a force over a span of time. This interaction is called impulse. Extending the time of an impact lowers the peak force, which is how airbags and crumple zones reduce the severity of a crash. By tracking energy states and momentum exchanges, you bypass the need to calculate the complex, real-time forces occurring during rapid interactions. Rotational physics maps the foundational laws of linear motion onto a circular path. Instead of pure force, we calculate torque. Torque is leverage. Pushing further from the pivot point increases the effect of the force, and the rotation is strongest when your push is perpendicular to the lever arm. When objects race down an incline, mass distribution matters. Rotational inertia describes how hard an object is to spin up. Because the hoop's mass is concentrated on its outer edge, it has a higher rotational inertia and loses the race to the solid cylinder. Oscillations follow a similar logic. Simple harmonic motion occurs when a restoring force, like a spring, pulls an object back toward a center point with increasing strength as it moves further away. Energy trades back and forth as the object vibrates. However, the period, the time for one full cycle, is dictated by the physical properties of the system, like mass and spring stiffness. Pulling the spring back further increases the amplitude, but it does not change the time per cycle. Whether an object vibrates on a coil or spins around a hinge, it obeys the same diagnostic buckets we used for straight-line motion. Fluid mechanics applies these core rules to continuous, flowing materials. Archimedes' principle explains buoyancy. Notice the upward buoyant force vector on this cube. That push is determined exclusively by the weight of the fluid that the object pushed out of the way, not the weight of the object itself. Bernoulli's principle links motion and energy in a moving fluid. As this pipe narrows, conservation of mass forces the liquid to speed up. As the velocity increases, the internal pressure drops. Calculating the lift on a wing or the flow through a pipe is just the application of point mass physics to a continuous system. Firm, instructive tone. Conceptual understanding only earns credit if your answers match the scoring rubric. Graders look for specific formatting and habits when they evaluate your work. Draw the free body diagram even when it isn't explicitly required. When asked to justify an answer, write full sentences that name the governing principle, such as Newton's second law, and connect it to the physical situation. Always include units with your final numeric answers. Draw the picture, name the principle, trust the process. AP Physics 1 is an interconnected system where every unit builds on the same 3 diagnostic buckets.